Now, why do I want to look at this? Why do I want to compare these two effects? Well, kinematical corrections, things like time dilation and length contraction, they're not very hard to take into account. But multiparticle effects are extremely difficult to take into account. When you solve for one particle, well, sometimes that's possible. Two particles, that's harder. And when you're talking about three or four particles, well, you simply can't do it. So the complexity of the problem increases significantly when you add more particles into the problem. My guess is that maybe quantum field theory is very difficult because it's a multi-particle theory. This is actually true. It's a correct guess. Now, what I'm going to try to do to convince you of this is I'm going to try to demonstrate that the corrections coming from kinematics are the same size as the corrections coming from multi-particle effects. You have to include them both together. But including multi-particle effects is hard. And this is why quantum field theory is hard. So to start off, let's estimate how big kinematical corrections are. To do that, I'm going to take a look at the formula for relativistic energy. So if I have a particle moving with velocity v, and I want to know its energy, what is it given by? Well, here it is. E is equal to mc squared divided by the square root of 1 minus v squared over c squared. M is the mass of our particle, c is the speed of light, and v is the velocity which our particle is moving. Now, what we have in mind is we've got a particle it's not moving so fast that relativity is very important, but the first corrections of relativity are present. So what we're going to do is we're going to take v over c, and we're going to assume that this is much less than 1. In that case, v over c squared is very, very much less than 1. And the number that you see sitting in the square root is a very small number. And that means we can Taylor expand in that small number. So this is the kind of calculation that I expect that you can routinely do. So let me write down the answer. And I want you to make sure that you could actually do this calculation. So expanding this out, we would find mc squared plus 1/2 mv squared plus 3/8. Oh, that's a 3. Let me just improve that writing. 3/8 mv squared times by v over c squared. And then there would be a whole lot of other corrections. Okay, so look at the first term. This first term is Einstein's famous E is equal to mc squared formula. So this is the term I'm looking at. Einstein's famous E is equal to mc squared formula. It tells us that matter is equivalent to energy. This, for example, is what's used in the nuclear bomb. You can turn mass into energy. But for our purposes, it's a constant energy. In classical mechanics, you can always add constants to the energy, and that doesn't change anything. The zero of energy is not physical. You're probably familiar with the fact that potential energy can't be measured. It's only potential energy differences that we look at in classical mechanics. Of course, things change in general relativity, but we're not talking about general relativity. In classical mechanics, the offset of energy is arbitrary. So the 0 point of energy is arbitrary, and you can't think of any experiment that would be able to measure it. So that term we don't need to worry about. So I'm going to remove it completely. It's unphysical. Look at the next term. Well, the next term is 1/2 mv squared. This is the usual kinetic energy of a particle, and that's the energy that a particle has because it's moving. That's usually what you would have used for the energy of a particle that's moving. The next term, this is the first correction due to relativistic kinematics. So that's that term sitting over there. That's the first correction due to relativistic kinematics. How large is it? It's 3/8 times nv squared times v over c squared. So I can summarize this by saying that this looks like a term of size mv squared plus a term of size mv squared times v over c squared. So what sets the size of the relativistic corrections? Well, they come with the size v squared over c squared. And I'm going to summarize that by saying kinematical corrections are of size v squared over c squared. This sentence summarizes the calculation that we just did. So you know exactly what I mean when I say it's of size v squared over c squared. I mean, take the correction, divide by the first term, and you'll have something of size v squared over c squared. Good. Now I want to calculate the size of multiparticle corrections, and I'm going to try to show you that they are the same size as kinematical corrections. So that's what we're going to try to do now. So I imagine I'm calculating some energy. So to calculate an energy, I should tell you what is the Hamiltonian. So the Hamiltonian, I will imagine, is H naught plus some coupling multiplied by H1. The important thing about H naught is that I can solve for the eigenstates and eigenenergies of H naught exactly. So H naught acting on eigenket n is some energy En acting on eigenket n. Now these are not the energies and kets of the exact Hamiltonian. They're the energies and kets of the unperturbed Hamiltonian. And to remind you of that, in our notation, we're going to include a subscript naught. So these are not eigenstates of the full Hamiltonian, they're eigenstates of the unperturbed Hamiltonian. Here, I'm using Dirac's Bra-Ket notation. I hope you are familiar with that. If not, well, you have some reading to do, and you should ask some questions. The problem that we actually want to solve is the energy eigenvalue problem of the full Hamiltonian. And we know that En, if we're doing perturbation theory, we'll be expressing En as a series. The first term is just the unperturbed energy, but then there will be a correction proportional to the coupling G, another correction proportional to the coupling G squared, and so it continues.